In this video, we'll be solving this geometry problem involving pentagons, translations, and triangles. Here's the problem statement. A pentagon ABCDE is translated north by 40 units to pentagon A1, B1, C1, D1, E1. Pentagon A1, B1, C1, D1, E1 is then translated east by 50 units to pentagon A2, B2, C2, D2, E2. We know the perimeter of the pentagon is 30 units. Find CC2. Okay, so they do talk a lot here about these different pentagon names, so let's go ahead and start off by interpreting what the problem is saying with the translation. So, a translation is when you take one figure, which could be a polygon, could be a 3D solid. In this case, it's just a regular pentagon, 2D shape. You take that shape and you basically move it to a different location. You move all the points comprising that figure, all 5 points in this case, and you move all of them by the same amount to get to a completely different location. Now, it's important to consider that with translations, you are not changing the area or the volume or anything, any of the side lengths. All of that remains the same whenever you translate a figure. So that's a central principle of translations right there that you must remember. Okay, so let's go ahead and start off by drawing our pentagon ABCDE. Okay, so let's go ahead and use black for this so we know. And this is just going to be a very basic drawing. It's not supposed to be accurate, but just a visual representation here. And they didn't say equilateral or anything, or equiangular. So here's ABCDE, very poor drawing, but it'll work for this problem. So, and then they say, translated north by 40 units to pentagon, this different pentagon here. And remember, it's going to be the same exact side lengths, same exact area. It's the same shape, just moved at a different location. So we're going to go up. We're going to go north by 40 units. We're going to put the new one up here. Try to draw it as similarly as possible so you can see. It's the same exact pentagon as before, but now it's just a different location. So we have to put the 1, the subscript, to indicate, to differentiate between these two pentagons. Okay, so then they say it's translated east by 50 units. Okay, so we're going east now with this pentagon, and it's still the same exact shape, same side length, same everything. But now, of course, it's over here. And we have A2, B2, C2, D2, and E2. Okay, so we've got 3 different pentagons here, and they want to know the distance CC2. So let's go ahead and figure this out. So CC2, we're going to start here at point C, and we're going to go all the way up here to CC2. So our line segment looks like that. That's CC2. Okay. Now, they also tell us the perimeter of the pentagon is 30 units, but in actual fact, that's irrelevant information. We don't need to know. We don't care what the perimeter of the pentagon is, because, as you can see, what if we go ahead and draw a line segment connecting the other points? We already have CC2. What if we connect CC1? What if we connect C1 and C2? So we get kind of a triangular figure here. We've got a triangle, 3 points, C, C1, and C2. So if we were to do that, we can now use the Pythagorean theorem to solve for the length CC2 right over here, because we know the other 2 lengths. They already tell us. We've got pentagon is first translated north, translated up by 40 units. This is our translation right over here, going from C to C1. And since all the points move by the same amount, we know that the segment CC1 must be exactly 40 units. So that's one side of this triangle. Then up here, we have C1, C2. We're moving east. We're moving to the right by 50 units on this diagram. So we know, similarly, that C1, C2 must also be 50 units. So, this here, we're going to be able to use the Pythagorean theorem to solve for the hypotenuse of this triangle, CC2. Now, it's important to not get tripped up by the side lengths here. You might say, oh, we've got 40 and 50. Isn't that part of a 3, 4, 5 right triangle? Isn't the third length just 30 then? But no, in actual fact, that's not the case, because a 3, 4, 5 triangle has those same lengths, but in a different order. With a 3, 4, 5 triangle, the longest side always has to be the hypotenuse. And over here, the 50 is not the hypotenuse. The hypotenuse is what we're trying to solve for. We don't know what it is yet. So, we know we cannot just apply the 3, 4, 5 triple right here to this problem just yet. So, instead, what we're going to do is we're going to just bash out the Pythagorean theorem as normal. There's no better way to do it than just to run the numbers. Okay, so we've got two values. As you recall, the Pythagorean theorem is a squared plus b squared equals c squared, where c is the hypotenuse, the longest side, and a and b are the legs of the triangle. So, we know, since we're adding here, it doesn't matter if we put the 40 first or the 50 first, but we have 40 squared plus 50 squared equals some c squared. Okay, now 40 squared is pretty easy to figure out. It's just 40 times 40, which is 1600. It's something you could just memorize over time. Or you could view it this way, 40 times 40. You could do 4 times 4 first, that's 16. Then you add on the 2 zeros. That gives you 1600. Okay, then the same thing for 50 squared. 50 squared is a nice round 2500. And this all adds up to c squared. Now, 2500 plus 1600, that's just 4100. So, we know c squared is going to be equal to 4100. Alright, now we need to take the square root of both sides of this equation because we want to get just the c value, the length of the hypotenuse. So, we take the square root of both sides. So, we have square root of 4100 equals c. Now, you might be wondering, okay, what are we going to do here? I mean, there's got to be some simplification involved. Yes. So, to simplify a square root, here's what we're going to do to get to the simplest reduced form of this. So, we must factor out a perfect square from inside this square root to get it into simplest forms. Essentially what we're trying to do here. So, we see right here, 4100, we've got those 2 zeros on the end. And those 2 zeros right there tell us that we're going to have a factor of 100 going into 4100. So we know right away that we can pull out the 100 because 100 is a perfect square. It's 10 squared, 10 times 10. So we know whenever we pull out a perfect square, we have to take the square root as it comes out of the square root. So 100, square root of that is obviously 10. Then, inside the square root now, we have whatever 4100 divided by 10 is, and that's easy. Just clip off, or divide by 100, that is, because we're pulling out 100. So we just clip off 2 zeros, because you divide by 100, and you're left with 41. And that right there, in fact, is our answer. So we simplified the square root down as our final step, and we got down to 10 square root 41 as our final answer for this question mark length, the length CC2. That's the hypotenuse of the triangle, and we have successfully solved this pentagon problem. So, essentially all we need to do there was use the fact that translations preserve size and shape, and that each point in a shape that's translated is moved by the same amount as every other point. From there, we've recognized that we have a triangle here, C1, C2. Then, we use a Pythagorean theorem to get the side lengths of each of the hypotenuse of the triangle, given the lengths here, 40 and 50. Okay, and that's all for this geometry problem video.